if they say, what is the value of bending moment and shear force diagrams? Well, they help us to identify maximum bending moments, right? Without a maximum bending moment, we can't find the bending stress, right? We can't find the bending stress we need to design for. Another thing we can do is we can see the direction of the graph. We can see where top steel is needed, right? We can see where steel needs to go on the top. That's a really important thing. So even if we just know the maximum, if we just took the maximum in this diagram, they didn't tell us anything else, we wouldn't know that we need top steel. Also, we could see that maybe an alternative is that we might change the loading conditions. We might change the spacing of these things. We might redesign to move walls and different load-bearing structures. We might change the layout of the design so that we don't have large forces. A third option we have is that we can change the material. We can say, you know what, concrete's just not going to work there, let's use steel instead. Or let's use a stronger concrete. Like let's use some admixtures and put more cement into the mixture to get better results. So that is why we draw these bending moment diagrams. Now that we know why we draw bending moment diagrams, we're going to start doing some examples. The last thing I'm going to do, just before we move along, is we're going to prove, again, that we can find the bending force at any location. Now, when I was talking about this, we imagined, this was with my class, they said, let's imagine that someone comes along and they say, you know what, I want to find this location at this point here. We called it the H number because the student's name started with a H. At location H, the client says, I had a bad dream that something was going to go wrong 1.5 meters from the edge. I just want to really know how much the bending moment's going to be there at that location. And just to make them stop talking, you say, you know what, we're going to find the sum of the moments measured at point H equals 0. And we know that that's going to equal left-hand side plus right-hand side. So, what does the left-hand side look like? If we take the left-hand side, it's going to look like this. We're going to have 5 kilonewtons going up, and then we're going to go across 1 meter, and then we're going to go down 6 meters, and then we're going to have 0.5 to point H. Yeah, we okay with that? To location H. So let's see what that looks like. We can say the left-hand side equals 5, is it clockwise or anti-clockwise? Clockwise, so we're going to say plus 5 times, how far away is it from point H?
0.
How? 1? 1.5, well done, thank you very much. 1 plus 0.5 meters away, or 1.5. Okay, so 5 times, and then we also have one more force. We have 6, is that going clockwise or anti-clockwise? The 6, anti-clockwise. Okay, and it is 0.5 meters away. So 5 times 1.5 equals 7.5, is that right? Yeah, I think so. 7.5 minus, what's this one going to be? 3 equals 4.5 kilonewton meters, because kilonewtons multiplied by meters. Now, often we don't see this result showing up a lot. When we do our reactions, we don't see this result because we end up dividing by meters again. But here, when we need to know what the internal force is, the internal bending moment in this case, we're going to have kilonewton meters. Okay, let's have a look at the right-hand side. The right-hand side is even more complicated. So we go half a meter across, go down 6, then we go across a meter, and then we go up 10, and then we go another meter and down 3. Okay. So what does that look like? So the right-hand side equals, well, first of all, we have 6. Is that going clockwise or anti-clockwise? Clockwise. So 6 times 0.5, and then we have 10. Is that going clockwise or anti-clockwise? Anti-clockwise, so we're at minus 10. And how far away is it?
1.5.
1.5. We didn't fall for that twice. Okay. And then finally, we have our third force. It's 3. Is it going clockwise or anti-clockwise? Clockwise. And how far away is it?
2.5.
2.5 meters. Exactly right. I thought I was going to get you there. I really did. Okay. So we have 3 minus 15 times 3, 4.5, right?
Wouldn't it be more than that?
3 times, oh, sorry, you're right. I multiplied 1.5. 7.5, is that right? I think that's right. Okay. What do you got? Calculator, add the whole thing up, and what do we get? Negative 4.5 kilonewton meters, right? Or anti-clockwise. So if we then take left-hand side plus right-hand side equals 0. So the sum of the forces was 0. It's true, they were 0. The sum of the forces were truly 0. But the thing is, the left-hand side and the right-hand side still had a magnitude, and that's what matters. That's how big is the arm wrestle, right? The arm wrestle at that location was pretty high, whereas the arm wrestle at this location is 0. Right? The arm wrestle at that location is 0. Now, generally, we don't have to find an arbitrary location, right? I don't think I've ever seen a HSC question where they said find the bending moment at location H. But if we had to, we can. We know how to do that now. The other thing we could look at is, often, if I was doing this as a professional, I would just look at the diagram and just say, well, it's halfway between 4 and 5. It's probably going to be 4.5. Because in this case, it's a linear thing. One last point that I want to say before we move on is, can you notice that our maximums and our minimums occur where we cross the axis? Now, I don't know if you've done this in calculus yet, but did you know that maximums and minimums happen where y equals 0? Okay, well, so that's something that you'll end up seeing in calculus. You'll say, oh, that makes sense now, that we can find maximum and minimum points wherever we cross the axis. So that can help us to solve HSC questions. We're going to look at some HSC questions, and we're going to say, where do we think the maximum bending moments are going to be, the minimum bending moments are going to be. Okay, we've gone into a fair amount of detail there. I really should take. I actually have taken photos of these when I did this with class. Okay, so we're going to keep going, and we're going to look at some more Copeland questions. Not for ages, like 2:30. Okay, I've deleted the thing, but that was the answers that we got. The shear force diagrams, the bending moment diagram. So Copeland is finding the bending moment at every single location. That was what our diagram looked like. We said we had a maximum of 5 and a minimum of -3, so that's the negative steel that we need. We found that at point location H, it was 4.5. Okay, and then Copeland talks about how you can just take the sums of the areas. Okay, so Copeland's got another question for us to do. I am going to draw this up, and then I'm going to close it. That's what I'm going to do. Okay, so let's have a look at our beam. Again, this is obviously another cantilever beam. I have spoken to Copeland, and he says he loves a good cantilever. Right, so here we can see we have forces outside of the reactions. Bless you. Okay, so if I'm drawing our free body diagram, what does that look like? Well, we have 4 down, we go across 1, we have reaction A, we go across 1.5, we have 6 down, we go across 1.5, and then finally 1 more meter, we've got 7. Okay. Now, in this situation, we should be able to calculate the reactions. That's something I might set for homework, is do this whole question, including calculating the reactions. In this case, we have the benefit of they have calculated the reactions for us. It's not symmetrical, so we do need to do the work, and that's going to be time consuming. If you don't know how to do reactions, watch my other videos or let me know. Okay, so that's our shear force. That's our free body diagram. The next thing we need to do is do a shear force diagram. Just because I might need that space. Okay. Shear force diagram. So I've got my line here. Yep. Where do we start? Tell me the story of this shear force diagram. Once upon a time, there was a shear force diagram.
And then it goes down,
it goes down 4 kilonewton meters, yep, then it goes across a meter, and what happens?
Up 8 meters.
It goes up 6. So if it was at -4 and it goes up 6, where's it going to be?
2.
2. Positive 2. Okay, positive 2. Then the shear force diagram kept on walking. How far is it going to walk? 1.5 meters. Okay, so we said it was at 2. And then something scary happened and it went down again to -4, back where it started. It's like a roller coaster for this shear force diagram. Then what happened?
It went up 11.
Went up 11. That didn't really line up. I want to try and get my forces to line up. Okay, so -4 plus 11 is what?
7.
7. Yeah, okay, so... And that's my diagram. This is maybe a little wide. Okay. That's my diagram. And in the end of the story, it ends up right back where it started. It was a bit like this song where this guy, he goes to a dance thing, and he sees this pretty girl, but he's like, nah, he gets, some guy comes along and sort of shoves him away. But then the girl's like, hey, why don't you come with me downstairs? And he's like, that sounds good. But then the guy chases them downstairs, but then his buddies, they come along and they fight the guy, and the couple run off, and things are looking pretty good. They're all happy and excited as they're running off, and then a truck comes and swipes them. Anyway, so it's a bit of a roller coaster, but I mean, in this case, maybe they stopped just close enough to end back at 0 and not in the negative. Okay, so I've done our shear force diagram. We're going to call this 1, 2, 3, and 4. Yep. Okay, so we're going to do our bending moment diagram. Now we have 3 different places where our maximums and minimums could be. Yeah, so that's not super useful for us, unfortunately. This is such a topsy-turvy story that it's hard to predict where our maximums and minimums are going to be. I'm thinking this is looking pretty dramatic, so we might have a maximum in that location. Let's have a look. What is our situation? I would just say that when I was at uni, they did always say it helps to really think about the beam as imagine what kind of shape it's going to have. That shape, if we just have a look again here, and I've heard other teachers when I've done marking and things, that they've talked about this as well, that it's actually not a bad idea. They even suggest getting a ruler and trying to sort of predict what it's going to look like. These are big forces here at the end. So it's probably going to be little and then big, something like that. That's probably going to be what it looks like. That's what the deflection of the beam is actually going to look like. And we've seen already that our diagram usually looks like the opposite of that. So that means our diagram should probably look like something like that. Yeah? I don't know where the line is going to be, right? I don't know where the 0 line is going to be, but it's going to look something like that. That's my prediction. So, okay, now that we've done that, keeping in mind that our maximum and minimums should probably be happening somewhere around here. Let's see how close we are to my bending diagram prediction. Okay, so what happened to my beam? That's the 0 line for our bending moment diagram. What happened in block A, in block 1?
-4.
-4 times 1 meter is -4. Yeah, so -4 times 1 equals -4. Okay, then what happened next in the story?
Then it went up 6.
Okay, 2 times 1.5, yeah? 2 kilonewtons times 1.5 meters, 1.5 meters, 1 meter. Yeah, I'll write in all the values, that make it easier for everyone. Okay, so 2 kilonewtons times 1.5 meters, yeah? So what's that going to be? 3. So that's going to take us to -1, yeah? Let's write that down. So we had -4 plus 2 times 1.5 is 3, right? Which equals a total of -1 kilonewton meters. Then what happened next in the story?
And after that, it went down 6.
Went down 6, yeah? So minus 4 times 1.5. So let's have a look. We're already at minus 1. Minus 1 plus minus 6 is? Minus 7, yeah, next 7. Okay, so we're going to write that down here. We're going to write minus 1 plus minus 4 times 1.5 equals minus 7 kilonewton meters. Okay, now the other thing to remember is you can always check if you've done something right or wrong. You can always check if you've done something right or wrong by if it adds up to 0. So let's look at the end. We're at negative 7. What's this? What's the area of block 4?
1 times 7.
1 times 7. So we had negative 7 plus 7 times 1 equals 0. And that's what we expect. That's our story. So where is our maximum?
7.
It's here. Does my diagram kind of look like a mirror image of that diagram?
Kind of.
It kind of does. And that can be a helpful tool to see if you've just done something completely wrong. Yeah? Okay. That's been good. Let's move on to our next one. I don't think there's anything else we really want to work out here. We would design our beam for this value, right? We would set for this value, when we would take our question, so we'd say sigma b equals m times y over I. The value we would use for m, we would use is 7 kilonewton meters. We wouldn't write minus 7 kilonewton meters, we just care about the absolute value. We can't have negative steel. Yeah. Well, we do have top steel versus bottom steel, that is true. Which means that actually what this needs, this whole beam probably actually needs top steel. All of the steel would be located in the top of the beam. So that is worth mentioning. And that's where these diagrams are important. If someone tells you, well, 7 kilonewton meters, if you don't need to know where the steel is located, that's a question. I can't say that I remember seeing anyone write that on their exams, but I would definitely give marks for that. Okay, I'm going to clear this off and we're going to look at the next question. Okay. Who saw that bus coming, the truck coming? Nobody. Okay. Okay. This next question is pretty important. Way back when we were learning about reactions, we learnt that rollers are the simplest. They just want to roller skate and just have fun, right? They're innocent little kids that just want to roller skate and have fun. Pins, they're a bit more mature, and that they can take more complicated forces. They can take horizontal and vertical, they can take perpendicular and parallel forces, they can take a diagonal reaction. And then we said the most advanced, right, the most serious was fixed reactions. And fixed reactions, not only would they take a diagonal force, a parallel perpendicular force, is that they could also take a moment. Now let's see what that means. In this case here, we have a balcony that sticks out past the wall of the apartment, right? There's no walls that hold up this balcony. The balcony is just sticking out there as a cantilevered beam. Now what we need to do is that not only is there going to be a vertical force, but what happens is if we have a force like this, let's imagine we had something that was like this, 2 and 2 and 4, it balances. The sum of the forces vertically are balanced, yeah? But the moments aren't balanced. Some of you may remember from the year 11 course, or maybe not, that if you don't have your forces balanced, what will happen is that this beam will start to spin forever because there's nothing resisting it. So Vicky, the fixed reaction, can also have a moment force that balances this force, and that's something that we're going to look at. Yeah, that's what we're going to look at in this diagram. Okay, our diagram was pretty close to that. So let's have a look at our free body diagram. Our free body diagram says we've got 200 millimeters and then another 100 millimeters. I'm going to write that in meters just because that's what we're kind of used to at this point. And we've got 2 kilonewtons and then another 3.5 kilonewtons. And then we draw our fixed reaction like this, and we say our reaction there, and we know that there's going to be some sort of moment reaction, right? Now we could call that, I'd call that the moment at the wall. I'd label it W. Copeland labels a couple wall. It's a moment couple force. You don't need to worry about that too much. I'm going to call it MW for the sake of it. So that's my diagram of what it's going to look like. Now I probably don't really need to show that it's fixed, but I find that's helpful to remember what's going on. Technically R is acting here, so the reaction, I'm going to write vertical even though there is no other force. I'm going to write vertical just to help me remember. Okay, so that's our shear force diagram. Not our shear force diagram, that's our, what kind of diagram is it?
Free body?
Free body diagram, excellent, thank you. The next diagram we're going to draw is the shear force diagram. Okay, so what is the value of R? So we said 2 down and 3.5 down. What is R going to equal? R equals 5.5. Yeah, that seem reasonable? Okay. Now, once upon a time, there was a diagram, and we had to go effectively what we do is we draw it in the negative. Okay. 5.5 times 0.2 meters. And then what happens next in the story? Goes down 2, and it keeps going across until it goes down 3.5 kilonewton meters at 0. Yeah, we good? Okay. Then, let's draw the story of the bending moment diagram. So we're going to call that area 1 and area 2. You okay with that? Okay. Now, the thing is, what we have to figure out is what is this value of MW? So what we're going to say is the sum of the moments at the wall equals 0. So 0 equals MW, right? Because there's some force going on there. And then we're going to have, what's our next force? 2 meters. Is it going clockwise or anti-clockwise? Clockwise or anti-clockwise? Clockwise times 0.2, and then another clockwise 3.5 times 0.3. Okay, you guys got calculators? I put my one down over there. So what we're going to say is that negative MW is going to equal 0.4 plus, is it 1.01 or something like that?
1.05.
1.05, that makes more sense. Okay, so our total reactions, we're going to say that equals 1.45 kilonewton meters, and it's going to be going anti-clockwise, yeah? Because we've got a negative answer. So let's start off by drawing our diagram, our bending moment diagram like this, and we're going to start off by, first thing we have to apply is, before we get to area 1 and area 2, is we have to apply that negative moment. And so our negative moment is minus 1.45. And then we look at what is in block 1. What's that area? 5.5 times 0.2 is? It's 1/5, right? So it's going to be 1.1. So what that's going to look like is it's going to look like this. It's going to be 1.45 minus 1.1 equals, it's actually plus, that's how we're doing it. Minus 1.45 plus 1.1 equals 0.35. And it's negative, yeah, that's right. And then finally, what's this area? 0.35. I don't think I drew the steepness of my curve properly. It should be more like that. It looks something like that. So that's how you draw a cantilever beam. These questions are very rare in the HSC. Very rare. Although Copeland talks about how much he loves cantilever beams, this, a fixed cantilever beam, I think in, say, 20 years, I've seen maybe two in 20 years, something like that. Okay. Moving on to the next one. I think we have one more in the book, and then we can finish up for this unit.
Will we go to this?
I mean, really, beginner, amateur hour. Okay, can you see that diagram? Yeah, looks pretty much like what I drew. Okay, we're learning about neutral axis and outer fiber stress. I've already done this in the bending intro, right? I'll quickly mention it very quickly, but okay. I'm saying this away from the camera. I don't even know if the camera will pick this up. That's a bit messy. Radius of curvature, pretty much never used. I mean, like, it's possible. I'll show you my steel design codes do use it, but generally we don't. We're not interested, right? We do care about E though, Young's modulus. Okay. Okay. So, you guys have got calculators?
I have the one on my phone.
Okay. So, what is our formula for bending stress?
My eye over.
Okay, we know that bending stress equals my over I. What does M stand for? Well, all right, sigma B equals bending stress. Bending stress is measured in pascals, but we use the Greece units. We go together like megapascals and millimeters squared. Okay, what does M stand for?
Moment?
M max, right, is how I would probably write it. I won't write that underneath, because otherwise I'll run out of space. Equals bending moment. And typically, we're usually interested in M max. Yeah? That's what we're typically going to be interested in. That is measured, oh yeah, we'll write that. It's measured in kilonewton meters, but we want to convert that to times 10 to the 6 Newton millimeters. Yeah? Have you done scientific notation yet?
Yeah.
Yeah, okay, great. Okay, so Y, which at uni will be called Y bar, is the distance from the neutral axis to extreme fiber. What does that mean? The extreme fiber. We're going to talk about that in a second. It's measured in millimeters, right? And then lastly, we have I, which at uni you'll call IXX, and that has two names. It can be called, we call it the second moment of area. But it is also known as the moment of inertia. That's what I learned at high school. And the advantage of that is it's got the letter I in it. But I remember when I was at uni, I had a lecturer who's like, no, that's not correct. Or maybe it was like, that's more correct. And that will be given to you in an exam as times 10 to the negative 6, 10 to the negative 6 multiplied by millimeters 4. Now, if I was maybe a little less lazy in this recording, maybe I might look up that if you're using a steel beam, when you buy it from the shop, they will tell you the moment of inertia. They'll tell you a whole bunch of the properties, or the second moment of area. They will tell you that. You can buy charts, or actually for $50 when I was a student, you would register for the Australian Steel Association. I can't remember what it's called. They then would give you a book with all of the tables. I have that book in my classroom. These days you can just look it up. If you know that you're dealing with a UB 610 something, or 610 UB 130, or whatever I have no idea what the kilogram weight of a 610, I'm making something up, right? They will then give you, if you look that up on the internet, it will tell you the second moment area of that shape. Now, at uni, eventually you will have to be able to calculate that on your own. Right, for timber, for wooden sections, right, timber sections that are rectangular, it's not that hard. And sometimes, for an example, I might write something up and I'll come up with an example on my own. But it's not that hard for timber to calculate. But for you guys, you're not there yet, you don't need to worry. Now, what we need to discuss is a little bit, is we need to talk about what the Y value is. Y is the distance from the extreme fibre. So let's just quickly revise. We know that if we bend a beam like this side is going to be in what's it going to be in?
Top side will be in compression.
Top side in this case is in compression. The bottom is being stretched, it's in tension. Now, somewhere in the bottom of this, usually for a symmetrical section, right in the middle, there'll be something called the neutral axis. So let's have a look at this. If we just pick this slice, right, if we just pick that section, we'd say at that location, we're going to have maximum compression at the top. And at the bottom, we're going to have maximum tension, yeah? And then somewhere in the middle, for a rectangular section right in the middle, we're going to have, phone down please, we're going to have no stress, yeah? We're going to have no stress in that middle location, yeah? And that's because it's at the neutral axis. We can then say that we can figure out that there's less compression here, there's less tension here, we can draw a diagram that looks like that. Now, the Y value is the distance from the neutral axis to the extreme compression, right? The molecule of steel, or the atom of steel that is in most compression or most tension, yeah? So this is YC, and this one here is in YT. Are you with me? Yeah, you understand what's going on? So in this case, for symmetrical sections, often, if we have like a rectangular piece of timber like that, right? And I tell you that it's 150 tall, and it's 50 wide, what do you think the Y value is going to be? The neutral axis for a rectangular section is going to be in the middle, right? So in that case, we call these letters B and D. I don't know if you knew that. Right? We call this the breadth and the depth. Yeah? Okay, so in that case, Y is going to equal, well, YC is going to equal YT, and they're both going to equal D on 2. Yeah? That's what they're both going to equal. Now, sometimes, like in this case over here, we get weirdos. See this shape here, T, the neutral axis is not in the middle. The neutral axis is much closer to the top. If I was drawing this diagram, that same force diagram, what it would look like is here I'd have an area of tension, and then it would go down and then suddenly go like this. And even though it's steeper than that, it's going to have to be bigger. Okay, so even though this is wider than that, the area of compression and the area of tension are equal. Can you see that? I mean, I've even drawn it perfectly, but that's the concept we're looking at, is that the area, I mean, I've also just done it, I've eyeballed it, right? But the area of compression and the area of tension, they will be equal. But what that means is, in order for them to be equal, right, it means that the neutral axis has to be a little bit higher. Yeah? In order for them to be equal, the neutral axis has to be higher. Yeah? In order for it to be equal. Okay. Now, what that means is that the y for compression and the y for tension, they are not the same. YC is not the same as YT in this case. Now, if you're a designer and you just want to make sure the beam is strong enough, which one do you care about? Do you care about YC or YT? You always care about big Y! Yeah? Always take big Y! Yeah? That's what you should take. Now I say that knowing that there was a past HSC question where they said, in this beam, calculate the compressive stress. And I'm sure there were students who looked at that question. It was the number 20 in the multiple choice, which is usually the hardest question. There would have been students who looked at that and said, but it's not, there's no compression. It's bending. There's no compression. They would have looked at it and they would have said, it's bending. That compression is an axial force. I don't understand. I don't know how to do this question. And maybe then they divided by the area or they got it wrong. But what they wanted people to do is instead to use YC, even though it was smaller. I do not like this question. I don't think it makes a lot of sense for an engineer. If they had said find YT, I don't think it would have been testing students too much. But I guess what they wanted to do, they wanted to see if students understood that bending includes both tension and compression. That's probably what they wanted to see. Okay. Our question doesn't ask that. Our question says how determine the bending stress in this beam. In which case, if we want to find the maximum bending stress, because bending stress is going to be different here to here to here. We're going to have maximum bending stress at this location, and we're going to have no bending stress at that location. And there's not going to be anything here either. If we imagine what is the deflection going to look like, the deflection is going to look like that. That's how this beam is going to deflect. Okay, and there's just no stress or bending at all happening past that location. Okay, not for a simply supported beam. Okay. What are we going to do? So first of all, we need to find the maximum bending moment. Now, what do you think the maximum bending moment of this diagram is going to be? Is there any way we